So adding on to yesterday, what we were doing yesterday, just looking at end behaviors. Now we're doing a full sketch. This is rational functions, not reciprocal functions, very different from reciprocal functions. And we talked about this where a rational function typically has x on top and x on the bottom. X on the bottom is a big part of it, but it also has an x on top. And so these are pretty complex sketches. And so they take a while. The first one's going to take us a long time because we're going to go through it slowly, but eventually you want to be able to speed up the process to not take a half hour to do one sketch. If that happens, you're not going to finish the test, that's for sure. So on top of end behaviors and asymptotes, which is kind of what we were exploring yesterday, we're also going to add in intercepts, and that's going to paint a picture of what these functions look like. Okay, so let's get started. Because this is such a long procedure, I like to have a real strict order of how I do things. If you're sort of thinking about how to get started, it's just adding on to how long it takes. And it's just not the ideal situation. So as you're doing your practice, come up with some kind of habit of the order that you do things, maybe even how you organize the information on the page, depending on if you write big or write small. That can be harder or easier. And depending on the question, sometimes some have a little bit more work than others. So again, that can be harder or easier, but it is something to think about. So I always start by taking, all right, I think we're working now. So first thing I like to do is it's useful to have expanded form and factored form. This one's a bit of an oddball because the top doesn't really factor. So that is a little bit different, but often they will. And so you fully factor the top, fully factor the bottom. The bottom is factorable. And we want to have both forms. So if you're given factored form, I would expand it. I think that's useful to have both forms. The expanded form is not quite as useful, but you will see that there's a couple of little places, and it's usually fairly easy. So having both is good. For those of you taking calculus, we do these kinds of questions again, but they get even bigger. And there's all kinds of other sort of steps, like algebraic steps that we do here before we move into properties. And again, this is just my habit of how I like to organize things. You don't have to do it exactly like me, but your solutions do have to be readable. I have to be able to follow them. They have to be organized in some way where things are clear. So, you know, it's something that's worth spending at least a little bit of time thinking about. But for these ones, we just need factored form and expanded form. And then what I like to start with is the intercepts. So the y with the subscript I, that's like a little I that's down low, means y-intercept. How do I find a y-intercept?
When the denominator is equal to 0?
Not when the denominator is equal to 0. That's a different thing.
Oh.
Nathan?
Oh.
Not sure? Aaron?
Put x at 0?
Sub 0 in for x, so y-intercept occurs when x is 0. That always works. The y-intercept is usually easy to find because you can just sub 0 in and put it in your calculator and hit equals, and then whatever it spits out at you is the y-intercept. It's kind of the easy one. And this is where we start to analyze, again, as things get more complex, this gets harder. Which form do I want to use? Do I want to use the top one, expanded form, or factored form when I sub in for x equals 0? Well, I want to use the top version. So I'm going to show this step. Normally, you're not going to. But for a lesson, it's a good idea to have it written down so that when you look back at it, you remember, oh, right, that's how we got that. So what happens to all those terms with the 0 in them? They're all gone. 0 squared is 0, times 3 is 0, times 2 is 0, right? 0 times anything, whatever, is 0. So we end up with negative 3 over negative 4, which is 3 over 4. That fraction is an easy one, kind of like we talked about in last unit. Having the decimal sometimes is better because we are going to be marking these things on a number line on the axes. And so, you know, knowing exactly what it is often useful. So 3 over 4, that one's pretty straightforward. But if you get 7 over 6 or something wonky, 8 over 3, it can be a little bit hard to know exactly what, like where that lies on the number line compared to an x-intercept or an asymptote, and things have to be lined up correctly. So putting the decimal in brackets like that is usually a good strategy. Okay, x-intercepts. Where do the x-intercepts occur? When y is 0. Like, that's the best straightforward answer. So every single kind of function that we're going to look at, how you figure out when y is 0 is going to be different, very different. For a polynomial, for a rational function, for a trig function, for a logarithmic function, for an exponential function, it's always going to be different. But that's the straightforward answer. X-intercepts occur when y is 0. Well, if I put y or 0 in for y, or f at x, if I put 0 in for that, when will the right side equal 0? When the top is 0. A fraction is equal to 0 when the top is 0, when the numerator is 0. That's when the entire fraction will be 0. What happens when the bottom is 0? Well, you can't divide by 0, so that's not equal to 0. So it's only when the top is 0. So we're going to set up this little equation, 2x squared minus 3 equals 0. If this was in factored form, you would just be solving a polynomial equation that's already factored. Okay, and I think we'll see that in, yeah, sort of other, well, we'll see it a lot in the practice and in future questions that we're going to do, but this one's a little bit different. This is where, again, things are complicated because you have to know how to solve all these different kinds of equations. What's the best way to solve this one? I'm going to isolate for x squared, so I'm going to move the 3 over, divide by 2, and then what? We're not done. Square root of both sides. What do we have to remember when we take the square root of both sides? There's 2 of them. Very good. And I am going to get the decimal version of this. Square root of 3 divided by 2. Approximately 1.2. How many decimal places do you need? I don't think you need more than 1. I mean, if you put 2, it's fine. That's not really part of your overall solution. That's really just for you so that we know, is it bigger than 1? Is it less than 1? Is it bigger than a half or 1.5 or something like that? Like an approximation for where it's going to lie. These are sketches, not graphs. When we draw them, it's not on graph paper. There's no grid. There's no scale. Sketch, this is just kind of like, these are words that I use. I differentiate between graphing something which is on a grid with a scale, accurate graphing, compared to a sketch, which is not on a grid, but you label important details. Intercepts, asymptotes, that kind of thing. Okay, so that's what a sketch is. So we just need to know approximately where we're going to put that, and we're going to mark it, but it doesn't have to be exact. Sound good? Got the y-intercept? How many y-intercepts are you ever going to have?
1.
You're only ever going to have one, because these are functions, and if you had 2 y-intercepts, you would have a point above another point, which is not a function. So you can't have more than one y-intercept. If you draw a graph, that's something you could think about. Did I cross the y-axis twice? If you did, you've done something wrong. How many x-intercepts can you have? It's technically infinite. Trig functions continue back and forth forever, and they always cross. We don't graph them that way, but technically you can have any number of x-intercepts. You could have 0, or you could have 1, 2, 3. We probably won't have really more than 3, I don't think, but anyway, right? But you could have any number of x-intercepts. This one has 2 x-intercepts, 1 y-intercept. Now we move on to asymptotes. Again, notice how I am organizing my work, making it clear where all the bits and pieces are, because these questions take up an entire page for one question. So if you're just randomly scattering your information everywhere, it can be hard to follow. I don't know if this sounds mean, but my rule of thumb is, like, if I have to spend more than 5 minutes trying to figure out what in the world you did, I'm going to give up. I say, I don't know, I can't follow this. Like, I try, but I can't follow this. So it is in your interest to make sure that your work is readable and that it can be followed by an outside observer. All right, I like to start with vertical asymptotes. I don't think there's a reason for it. This is what I'm saying. It's just the way I do it, but I think it's a good idea to have a way that you do it. How do we find vertical asymptotes? Vertical asymptotes occur.
Is it when the denominator is equal to 0?
This is right, very good. This is what we did yesterday, when the denominator is equal to 0. X-intercepts when the numerator is 0. Vertical asymptotes when the denominator is 0. See how you can get this stuff mixed up? And when you come into a question like this, you have to have a very clear understanding of where all the bits and pieces of information come from. Because if you get them backwards or mixed up, the whole thing is going to fall apart. You're not going to be able to draw the graph, and that's where all the big marks come from, right? So where the bottom is 0. If you want to make another note of that, just so you have it, there you go. Now, going back to our 2 forms, which one do we want to use to figure out where the denominator is equal to 0? Again, this is that whole thing where, like, the deeper understanding you have of all of this, you're not spending time thinking about it and wondering about it. You've done the practice, you're used to this procedure, and you know which one of, we only have 2 in this case, but like eventually in calculus, you're going to have at least 6 different forms of equations. 6. And you have to know which one you're using for which type of thing that you're doing. So, but we only have 2. Which one do we want to use to figure out where the bottom is 0? Nathan? The second one, because it's factored, and that's how we solve a polynomial. This is quadratic in this case, but that's how we do it, right? Where each of those brackets, 0 product property, where each of those brackets is equal to 0. Again, this is just me being sort of rigid, I guess, or whatever, but I like to work left to right. So I look at the x-intercepts and the asymptotes, because you can have more than one vertical asymptote, and I do them from left to right. The reason why I like to do this, and a lot of people I've found don't necessarily do it this way, But when I go to actually do the sketch, I am confident that I've done it left to right, so I know things are in order. So I just know where to find the bits and pieces of information. When we do the sketch, you'll see what I mean. Finding the information is important. So I'm going to start with the asymptote of x equals -1 first, because that is the one that's on the left. The other one is 4/3, which is like 1.3, right? What is a number just to the left of -1? This is all the stuff we did yesterday.
-0 or 1.01.
Good, -1.01. So I can sub this into my calculator, and if I put it in, I get -13.7, which is not a very big number, but I think I'm close enough to the asymptote that I can be confident that we're going to -infinity. Okay, so it's going down because we're in the negatives. 13 is not very big, 14 is not very big, but we're really, really close. It's not going to turn and go back up at this point. So as x approaches -1 from the left, y goes to -infinity. Whoops, -0.99 is just to the right. Again, when it's negative, sometimes you get those flip-flopped, and that can be a big problem. I'm going to go over this briefly now. I think it's going to be better in the next example, but I'll go over it briefly now, just because I think the more often you see this, the more it makes sense. I can look at factored form. 0.99 times 3 is going to be less than 3, right? Because 0.99 is going to give me, is less than 1, so 3 times 1 would be 3. So that's going to be negative. Negative 0.99 plus 1, well, that's going to be positive, isn't it? Negative 0.99 is less than 1. This one's the one that's hard. What's 0.99 squared? I don't know. Does anybody in here know what that is? No. But
I would be 81 over 100,000.
something like that, and that's good, whatever that is, which is 0.00 something. But it's less than 1, right? Like if you take a number that's less than 1 and you square it, it gets smaller. 0.5 times 0.5 is smaller than both of those. If you square a number bigger than 1, it gets bigger. If you square a number that's smaller than 1, it gets smaller. That is a thing. So I know that this is less than 1 times 2 minus 3 is negative. So I've got a negative and a positive. So just by inspection, this is a hard one. This is one where you might just want to put it into your calculator. Okay, and that is part of practicing and getting used to the different types. And the next one we'll have is going to be fully factored, and so we're going to do the inspection for every case. And when you can do it by inspection, it's a lot faster than putting it into your calculator. If you can program your calculator, that speeds things up tremendously as well. So there's all these little tricks. And folks, all I can keep saying is, if you don't employ at least some of these efficiencies, you are going to run out of time on quizzes and tests. So that's part of the expectation, is that you're practicing enough and you're figuring out the way you like to do it so that you can get it done in a certain amount of time and you don't need 3 hours to do one of these, right? That is part of this. So keep that in mind, and there's different ways of doing that. And you just have to get comfortable with the way that you're going to do it. So 2 negatives and a positive means this is going to work out to positive. Whatever it is, I know that it's positive. So as x approaches -1 from the right, y is going to positive infinity. What's our other asymptote? Good. Positive 4 over 3, which is approximately 1.3. So what's a number just to the left of that? When it's fractions and decimals, it can be a little bit tricky.
1.29.
1.29. Can anybody think of another one?
I'd probably say 1.299.
1.299. Now, technically, 4 divided by 3 is 1.3333333333, right? So what's just to the left?
1.32.
1.32, or even, and any of those are fine. Any of these numbers would work. So this is just kind of a number thing. 1.33 is less than 1.333333, right? If you truncate it, it is less than. So we don't even have to round the one down. We can just leave it at 1.33. That would be less than. If I punch this into my calculator, I get negative 23. What is just to the right of 4 over 3? 1.34. I like it. And when I do that one, I get positive 13. So again, not huge numbers for whatever reason. Usually they are bigger. But again, this is part of, when you do enough of these, you start to build this sort of familiarity and this comfortness with how these numbers work out, and you might be able to pick a mistake, like catch a mistake and say, wait a minute, that doesn't look right. That's never happened before. And double check your work, that kind of thing. If you don't do the practice, trust me, even if you think you get this, you're missing out on so much other stuff that can happen and does happen. And if you're trying to catch those mistakes on a test, or if something new comes up on a test that you've never seen before, it's going to be really, really tricky. All right, we've got our intercepts, we've got our vertical asymptotes and end behaviors. What's left? Horizontal asymptote. How do we find the horizontal asymptote? Yep.
Dividing our two largest x terms.
So what is it in this case?
2x squared and 3x squared.
So it's y equals 2 over 3. They have equal degrees. So it's a horizontal asymptote, and we take the coefficient of each. Remember, if the degree on top is less than the bottom, it's just 0 every single time. That's important to know. If they're equal, then we take, jumping around. Then we take the coefficient on top and the coefficient on bottom and just put them over each other. If the degree on the bottom is smaller, then it's an oblique asymptote, so that's what we're going to do tomorrow. Okay? The testing for horizontal asymptotes is different in two ways. What we put in, and then the output and how we interpret it. I cannot repeat this enough times. Vertical asymptotes, we really do only care if it's positive or negative, because it's either going up to positive infinity or it's going to negative infinity. Think about the behavior around vertical asymptotes. Both of those are going to positive infinity, but they could be going to negative infinity. So I'm picking values very close because my x is my input. I always pick x values to put in. So I can pick an x value that's very close, but just to the left or just to the right. What values do I pick to test for horizontal asymptote? This was one of the big takeaways from yesterday.
I like to use 100 and negative 100.
Big x values like negative 100 and positive 100. Very good. So we'll start, I always do left, right, start with negative 100. The other thing that's different about this is it's not whether it's positive or negative. Think about it. The horizontal asymptote is 2 over 3. I'm approaching the asymptote. Of course it's going to be positive. If you get a negative number, you got the wrong asymptote. You put negative 100 into this and you don't get a positive number, or you get like positive 10. Well, that's nowhere near your asymptote. That doesn't make any sense. You should be close to the asymptote at that point. So this one works out to, again, I'm just punching this into the calculator, 0.664, and then positive 100, 0.668. How do we interpret this answer? Very different from vertical asymptotes. We take these and compare to the horizontal asymptote. Are they above or below? So what are they? Good. So 2 over 3 is 0.666666 and so on. So 664 is below that, and 668 is above that. Again, you can probably imagine if these were negatives, how even more, again, confusing. There's all these little things that you got to be careful of. As x goes to negative infinity, y approaches 2/3 from below. As x goes to positive infinity, y approaches 2/3 from above. So we're already 25 minutes in here and we haven't even started sketching. Remember when I said the first one would take us about half an hour? There you go. Okay. But I think we're ready. We have our intercepts. We have all our asymptotes. And we have all the behaviors around the asymptotes. Now we have to put it all together. So let's do it. When you're doing a sketch, I mean, for your own notes, whatever, but on an assessment, you better be using a ruler to draw your axes. Absolutely, you have to put arrows on the end of each. This is just formatting stuff, but they have to be there. Label your axes. What's different in this case is you don't have to have a scale. You shouldn't have a scale. Putting a scale is going to make it harder. Don't do a scale. Okay? So no scale is needed, no grid. But make it look as nice as you can. And again, the more you practice, it might feel hard at first, but you can improve at this stuff. Again, this kind of just comes with experience, and as you work through the practice over the next several days, you'll start to develop your own style possibly. But I usually start with the asymptotes. So maybe it's safe to kind of, again, go by that, by my experience. Okay, so I've got an asymptote at -1. And at 4 over 3, so 1.3. So that's a little bit further out. And if anybody's wondering how much to scale these have to be, well, that's not very good to scale. They don't. I would like think about it a little bit. And if you've got 1 and 2, make it about double, but don't overthink it. You know what I mean? It doesn't have to be all the way to scale, but it's how you stretch things out and where you put things. You don't want things to be too tight together. You also don't want things to be too spread out and too big. Makes it hard to graph. So that's, again, where experience comes in. You have to label everything. So the label of the asymptotes is important. We've got another one. Y equals 2/3. The X scale to the Y scale is totally irrelevant. They do not have to match at all. They won't. Sometimes you're going to have a Y-intercept of -60 or something like that. So they're not going to match. Okay, so don't worry too much but you don't want things to be too squeezed together. That's for sure. You might, depending on how good of an artist you are, or how good you are at drawing graphs, you could put in your intercepts here. Sometimes I like to just draw the graph and put the intercepts in after. This is kind of maybe a silly thing, I don't know. But like if I put an intercept in and then I try to draw the graph and I miss it or something, then I have to go back and redo it, you know what I mean? So you can just draw the graph and then mark the intercepts after, but you want to have a sense of where the intercepts are. So we have an x-intercept at -1.2 and +1.2. -1.2 is somewhere to the left of that asymptote. +1.2 is somewhere also to the left of that asymptote. All of these pieces are going to fit together. Okay? And they're going to match, complement each other. We're going to come back to that when we're done. And go over that again. The last thing we need to do is mark our end behaviors. To the left of -1, I'm going down. To the right, I'm going up. So to the left, down, to the right, up. This one's the same, to the left, down, to the right, up. Notice how because I did it in that order left to right, and I always do, it's easy to read. I know everything. I know where it is. I know everything is in the right order. So it's easy to find the information I need. Off to the left, we're below. Off to the right, we're above. So to the left, we're below. To the right, we're above. I kind of pencil those in because I'm going to do my final graph like, you know, in pen or in darker pencil or whatever so that it looks nice. And I can erase those after, or they just don't show up as much kind of thing. So I kind of pencil those in. And now I think we're ready to draw it. Are you ready? This one starts here, has an x-intercept in there somewhere, and ends down here. So what does that look like? Something like that. Add in my x-intercept and label it. Look at this. There's no x-intercepts over here. It starts up here and ends here. So doesn't it just kind of go like this? Right? What happens in that middle spot? Starts up here. It's got a y-intercept of 0.75, which is above the asymptote. It's got an x-intercept in there somewhere and ends down here. Again, doesn't that all fit together and paint a picture of what's really happening here? And I go Something like that. And we're done. Any questions? It's a lot of work for one graph, yeah?
It doesn't matter that it crosses the asymptote.
So, very good. Functions can cross, and often do, horizontal asymptotes. They never, ever, 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 ever cross vertical asymptotes. Never. Okay? Horizontal asymptotes, yes. Vertical asymptotes, no. Some of you might wonder, and eventually you will, if you're not yet, how do I know it doesn't go like this? Well, they just don't. They never do that. Okay? If there was some kind of weird, I've never seen a function do that. If there was some kind of weird one, to know that it does that, you'd have to take calculus. That's how you would figure that out. So it's just a smooth curve. Always is for these ones. Sometimes they have turning points, but that will come out in the properties that we're detailing. Okay? Yeah. Okay, so I'm going to go through this one a little bit more quickly. But if you have questions, stop me. You know when you learn to factor and you just get like 50 factoring questions to practice, and the next day you get 50 more, and the next day you get 50 more? Well, we can't do 50 graphs. It would take all day, it would take forever, it would take you all weekend. But practice still does help. So, you know, going through the procedure over and over again. So now we're just going to kind of go through it more quickly, but we're just going to go over it over and over again for repetition practice to get better at this stuff. What's the first step? Whenever I ask that question, even if you don't put up your hand to actually answer, you should be thinking about it. Because when you do the quiz, when you do the test, that's what happens. Oh, what do I do first? Where do I start? What's the first step? Very nice. Factor everything. So the top is already factored because it's just linear, and the bottom is a simple trinomial, easy factor. And this is, now you're already probably starting to understand why I say having a habit of order of how you do things is so important, because what do you do next? There's lots of things you could do, but if you always do it the same way, well, next we're going to do intercepts. The Y-intercept occurs when x is 0. That means that's gone, that's gone, that's gone. I'm left with 2 over 12, which is 1 over 6, which is approximately 0.17. So again, looking at our two different forms, I chose the top form, expanded form. That's the easier one to get the Y-intercept. I just look at the constants, and it's one over the other. X-intercept occurs when y is 0, which happens when the numerator is 0, when the top is 0, which is at -2. Done. When I have everything in factored form and expanded form, I just go pick out the information that I need. See what I mean? How the x-intercepts are, usually you can factor everything. The first example was a bit of an odd one. And so you've got it factored, and you just start pulling the information out of there. And you don't have to show any work. You don't have to, I didn't even really have to write this twice. I just did, but because it's a lesson, but right? Like you just kind of go straight to your answer, 1 over 6. Straight to -2. Asymptotes. Vertical asymptotes occur when? No? Yes? Looked like you were going to say something.
X is -3 and -4.
When the denominator is equal to 0, right? Yep, no, that's good, but you gave them to me, that's fine, right? So that's when the denominator is 0, which is -4 and -3. Very good. So x equals -4. What's the number just to the left of -4? -4.01. And just to the right? -3.99. And then our other one, x equals -3. So just to the left of that is -3.01. And just to the right is -2.99. When I sub in -4.01, this is where we're doing the inspection this time. I'm not putting any numbers in because everything's factored, everything's friendly numbers, no fractions, nothing like that. It's going to be easy. Okay? -4.01 plus 2 is negative, plus 3 is negative, plus 4, well, -4.01 is a little bit bigger than 4, so it wins, so it's still negative. So I've got negative, negative, negative. 3 negatives makes negative. -3.99. X plus 2 is still negative. X plus 3 is still negative. -3.99 plus 3 is negative. If you can't follow this kind of math, if you're having a hard time following this, I mean, we can go over it again more slowly, but think about it, work on it, or just choose a different method, okay? And just punch it into your calculator, learn to program your calculator. If you're typing it out every single time, like I said, that's a really, really slow way of doing this. But this is something that I would imagine everybody can do once it clicks. So give it a try and see if you can figure it out. So still negative, but -3.99 plus 4, well, now the 4 wins, so now it's positive. So I've got 2 negatives and a positive, which means we're positive. -3.01 plus 2 is negative. Plus 3 is negative. Plus 4 is positive. So this is also positive. -2.99 plus 2 is still negative. But plus 3 now becomes positive. Plus 4 is positive. So I've got 1 negative, so this is negative. So as x approaches -4 from the left, y goes to -infinity. From the right, positive infinity. Positive infinity. Negative infinity. Finally, horizontal asymptote. Which is what? Zero. Y equals 0. Why? Because the top is degree 1, bottom is degree 2. So it's like 0 over 1. When the degree on top is less than the degree on bottom, it's always y equals 0. Very good. And again, these are the questions that you ask yourself. How do we do testing for horizontal asymptotes? Vertical asymptotes is numbers just to the left and just to the right. Horizontal asymptotes is big positive and negative numbers. This is stuff you just have to know. The more you have to stop and think, the harder it's going to be. This is not by inspection. This is putting the values into the calculator and calculating it and getting the actual value. So I've already done that, so to speed things up, I'm just going to write it down. These are both rounded. Whoops. So then I take these and compare them because, yep.
Couldn't you really just do it by inspection?
So the only reason why in this case you could is because y equals 0. And so if it's positive or negative, you could figure that out, but that's a special case. So other cases, by inspection, you can't say, is it 1.01 or 0.99? Like, you can't do that in your head, right? So you got to put it in your calculator. So I think you just always put it in your calculator. Because it's y equals 0, it ends up that it is just positive or negative. But usually that doesn't happen. So as x goes to negative infinity, because that was my negative 100, y approaches 0 from below. As x approaches positive infinity, y approaches 0 from above. Okay, I'm going to do my horizontal asymptote just because my ruler is horizontal. Ah. My vertical asymptotes are -4 and -3. I don't want them to be too squished together, so again, although you want things to be somewhat to scale, like I said before, they do not have to be perfect. You might just want to watch, copy it down after, or if you get a chance, or if you feel like you're already kind of getting this, then you go for it. You can do it yourself. Here's my end behaviors. Based on the information, left is negative, right is positive, so up, and then down. So down, up, down. To the left, I'm below. To the right, I'm above. So below, above. I only have one x-intercept. And it's over here at -2. No x-intercept on the other side. No x-intercept in the middle. All of that makes sense. That means these two go like this. Like there's no x-intercept there. These go like this. Again, doesn't cross over. But I have an x-intercept and a y-intercept that's positive. Y-intercept was positive. Positive 1/6. How does that information all fit together? Well, if my y-intercept was negative, I'd go like this, and then you'd go like this, and you go like this, and you go like that, and now you've drawn something that's not a function. It doesn't make any sense. Or you would just go like this, and like this, and like that, or something, and that doesn't make any sense because the x-intercept was negative. But why does this make sense? Negative, positive, and then approaching from above. It doesn't cross again. So just think about this for a minute. How all those pieces fit together. and that if the x-intercept, if I got it wrong and it was positive, this wouldn't work because I have to start down here, get up there, and then get back down here, and then get back up there. What if you did something like this? Well, now you've got all these extra, what I would call phantom intercepts. They don't exist. They didn't come from anywhere. What's going on? There was one x-intercept. There aren't going to be other ones. There can't be. There never will be. They're only the ones that we find algebraically. So it has to look like that. And if you are ever drawing one of these and something is feeling weird and you're like, wait a minute, what is going on? We've talked about this before, but like, what's going on here? Something's not adding up. Okay, something's not adding up. That's what that means. You've got an x-intercept on the wrong side of an asymptote, or you've got an x-intercept that's negative, but it should be positive, or vice versa, something like that. Okay, that is what that means. Oh, I thought we had one more. Any questions about that? Yeah. Great question. So the question is, how do you know where that turning point is? You take calculus. And in calculus, you'll learn how to find that point. We don't know, so just make it nice and smooth. I wouldn't go like this. You can't go like that because now you've added x-intercepts. If you went to here or you went down to here, any of those, whoops, are fine. It's not, we don't know, so just make it nice and smooth and make it look kind of natural. So this one looks like a complicated rational function like the ones that we've been exploring. Something happens when I do the first step, which is factoring. So this should be x minus 2, x minus 1. So what happens?
X minus 2 cancels out.
Those divide out, and I'm left with x minus 1. What does the graph of this look like? Well, it looks like that. And what is that? It's a straight line. It's got a y-intercept of -1 and an x-intercept of +1. And if I can get my ruler out here. But we talked about this yesterday when I gave you that big sheet with the definitions. When you have a common factor in the top and the bottom, that is a hole. What does a hole look like? Well, it looks like a hole. So we have a hole at x equals 2. From that factor. So what I do is I go to 2 and I erase a little bit and I draw a hole. And it's as easy as that, and that's what that looks like. And the weird thing is, when you pull out a hole, this original function looks like whatever's left over, except at that one point it's missing a spot. That's what a hole looks like. So it could still be a rational function that has all kinds of asymptotes and stuff. This one is just super simple. It could still look like that, but it's got that hole in that spot. That's how you draw those things.